Imagine a spaceship that moves not by engines, but by compressing the spacetime in front of it. This concept might seem like science fiction, but it's not entirely so. Physicists have been exploring the theoretical possibility of warp drives for decades, and a new study published in the Open Journal of Astrophysics takes this idea a step further by simulating the gravitational waves that such a drive could emit if it were to fail. Warp drives are a staple of science fiction, theoretically enabling spacecraft to travel faster than the speed of light. However, there are numerous practical challenges in building them, such as the need for an exotic form of matter with negative energy. Additional issues with warp drive metrics include their potential to create closed time-like curves that violate causality and the practical challenge of controlling and deactivating the warp bubble from within the spacecraft. This new research, a collaboration among experts in gravitational physics from Queen Mary University of London, the University of Potsdam, the Max Planck Institute for Gravitational Physics in Potsdam and Cardiff University, does not claim to have cracked the code for warp drives. Instead, it uses numerical simulations to explore the theoretical consequences of a warp drive failure. Dr. Katie Clough of Queen Mary University of London, the study's lead author, explains, while warp drives are entirely theoretical, they are well defined within Einstein's theory of general relativity, which allows us to use numerical simulations to explore their effects on spacetime in the form of gravitational waves. Dr. Sebastian Kohn from Cardiff University's School of Physics and Astronomy, a co-author, adds, Miguel Alcubierre created the first warp drive solution during his PhD at Cardiff University in 1990 and later worked at the MPI in Potsdam. Therefore, it is natural for us to continue the tradition of warp drive research in the era of gravitational wave astronomy. The results are fascinating. A collapsing warp drive would produce a distinctive burst of gravitational waves, a ripple in spacetime that could be detected by gravitational wave detectors typically aimed at black hole and neutron star mergers. Unlike the chirps from merging astrophysical objects, this signal would be a short, high-frequency burst which current detectors might not catch. However, future higher-frequency instruments could detect such signals. While no such instrument is currently funded, the technology to build them exists. This raises the possibility of using these signals to search for evidence of warp drive technology, even if we cannot build it ourselves. Dr. Kohn warns, in our study, the initial shape of spacetime is the warp bubble described by Alcubierre. While we show that a detectable signal could theoretically be observed by future detectors, the speculative nature of the study means this is not sufficient to drive instrument development. The study also investigates the energy dynamics of a collapsing warp drive. The process emits a wave of negative energy, followed by alternating positive and negative waves. This complex interaction results in a net increase in the system's overall energy, and in principle, outgoing waves interacting with normal matter could provide another signature of the collapse. This research pushes the boundaries of our understanding of exotic spacetimes and gravitational waves, Professor Dietrich comments. For me, the most exciting aspect of the study is the novelty of accurately modeling the dynamics of negative energy spacetimes and the possibility of extending these techniques to physical situations that can help us better understand the evolution and origin of our universe or avoid singularities at the centers of black holes. Dr. Clough adds, this serves as a reminder that theoretical ideas can push us to explore the universe in new ways. Even if we are skeptical about seeing anything, it's interesting enough to be worth looking. The researchers plan to explore how the signal varies with different warp drive models and the collapse of bubbles traveling faster than the speed of light. Warp speed might be far off, but the quest to understand the universe's secrets continues, one simulated collision at a time.